Today we have section 11.5, and what we're going to talk about today is lines and planes in space. So we'll be writing equations, obviously, of lines and planes in space, and then different things that we can do with them. So first thing we better do to start is to figure out how to write a line in space, and we want to use vectors to determine the equation of a line. There's two different ways that we can write equations. The most common is going to be the parametric equations of a line. And so remember, parametric, this goes back to chapter 10, sections like section 10.2 and 10.3. But when you have a parametric equation, that means when in two-dimensional sense we had x is equal to something and y is equal to something. Well, now obviously we're talking about things in space. Therefore, we're going to have x equals something, y equals something, and z equals something. So most common, we will end up having writing our equations of lines as a parametric equation. Well, in order to write the equation of a line, we need two things, just like we did normally if we have to write the equation of a line. We need a point and we needed the slope. Well, basically the same idea here is if we want to write the equation of a line, we need a point on the line, and instead of a slope, this time what we're going to look for is a vector, and this vector is called your direction vector, which to me it's the same type of idea as having a slope. So a parametric equation above here, what I'm going to try to squeeze in is when we write the equation of a line. So write the equation of a line. We need a point, and obviously that point has to be on the line, and a direction vector. Well, your direction vector takes the place of the slope. So our parametric equations, we have a line L parallel to this direction vector. So I've got a lot of side notes here. But this is considered to be our direction vector. Direction vector. And then your direction numbers are A, B, and C. And it has to pass through a point. And again, this can be any point that's going to be on our line. It's represented by these parametric equations. So our parametric equations, remember, need what is x equal to, what is y equal to, and we'll need what is z equal to, because this is a point, or I'm sorry, a line in space, so we need our 3 dimensions. Well then, what we do to create this, it's your point, your x point, plus your direction vector, your direction number here is a, that corresponds with that first coordinate, so it's a, and then times t, because remember parametric, we had that parameter of t. And then y is very similar, so for our parametric equation for y is equal to y sub 1, our point, plus our direction number, which corresponds to the, your y, so b times t. And then z is equal to z sub 1 plus c times t. And so this is generally, we're going to use parametric equations. So this is definitely the most common form of how to write the equation of our line in space. We can write a symmetric equation if our direction numbers A, B, and C are all non-zero. And why we can do this then is that we can eliminate the parameter t. So basically I'm going to solve everything for t, and as long as A, B, and C are not 0, t will be involved in every equation. But if one of them is 0, let's say A is 0, obviously then you don't have t for that portion of your parametric equation. So as long as you have t in each of them, basically we're solving for t. So then I can say that x minus x sub 1 divided by a, that's equal to t. And now to set this one equal to t, we have y minus y sub 1 divided by b, because that equals t. And this is equal to z minus z sub 1 divided by c, because that's equal to t. So it's eliminating the parameter t, and now here is our symmetric equation. Neither parametric equations nor symmetric equations of a given line are unique. What that means, if they're not unique, is that there can be more than one correct answer. There's not one unique answer to this. So this means that there can be more than one correct answer. There can be more than one answer. Alright, so a couple examples here. We want to find sets of parametric equations and symmetric equations of the line through this point. So negative 3, 0, 2. Obviously that has to be a point that's on the line. And it's going to be parallel to this vector. Well, when it's parallel, this is our direction vector then. And so you can write in here that here is our direction vector. And I kind of like writing it, writing my vectors out like this, where I know for my direction vector now it starts with I. Well, there's nothing there, so that would be 0, 6, 3. And so when I write my equations, first of all I have to write a parametric equation for A. So x is equal to my x coordinate there, so negative 3, plus my direction, my x direction, which is 0 times t. And I'll just list them this way for my parametric equations. Y is going to equal 0 plus my direction is 6 times t, and z is going to equal my z coordinate, so it's 2, plus the z direction would give me 3t. And obviously you want to make, clean it up. You don't want extra stuff in there. So x is equal to negative 3, y is equal to 6t, and z, can't do any changes with that, 2 plus 3t. So here would be our parametric equations for this line. Now for B, if we want to write symmetric equations, remember we're solving for t. Well, I don't have a t here in this first parametric equation, therefore we cannot do this one. Otherwise, solving for, or finding the symmetric equations, all you do is solving for t and set them all equal to each other. The next example, we want to move it up a little bit. We'll find the sets of parametric equations and symmetric equations again of the line through our 2 points. We have 5, negative 3, negative 2, and the point negative 2/3, 2/3, and 1. Well, again, in order to write the equation of a line, we need a point on the line. Well, we have 2 of them, and we need to figure out the direction vector. So our direction vector is really the first thing that we can do, or that we have to do, and that's going to be between these 2 points. So first of all, to find our direction vector, it's just basically it's your vector between the two. So then whatever order you want to do here, I'm going to take negative 2/3 minus 5. And negative 2/3, if I subtract 5, that's negative 17/3. If I take 2/3 and subtract a negative 3, that gives me 11/3. And if we take 1 minus a negative 2, that gives us 3. So here's our direction vector. What's nice about, well, it's ugly right now to start. I don't like having fractions. And really I just have to have a vector in this direction. So I'm going to multiply this by 3 because that's going to be a parallel vector, and it's still going to be the direction vector of it. But the nice thing is that I can avoid the fractions. So basically a direction vector, as long as it's parallel, you're good to go. So if I multiply it by 3, obviously then I have negative 17, 11, and 9. And those are much better numbers that I would like to use. Again, you don't have to do this, but to me it's a lot nicer. So then for A, I want to write a parametric equation. Well, I need what is x equal to, what is y equal to, what is z equal to. And here you can use either point. Well, let's avoid the fractions again. And so I'm going to use this first point, and this would be 5 plus that value, well, negative 17, so I'm going to change the plus to a negative 17t. Y, well, my y coordinate is negative 3. My direction vector is 11, so 11t. Z, I have negative 2. My direction is 9, so plus 9t. And there's our direction vector, and that's why these aren't unique, because you could have taken this original vector, direction vector, or we could have taken this point instead of this point. So really there are a lot of different ways that you can write the equation of this line. And yeah, there's usually one that works out a little bit nicer. We definitely would rather deal with integers than dealing with fractions and stuff. For this one now, we can write the symmetric equation because we have t in all of them. So basically, how do I solve for t? Would be x minus 5 divided by negative 17. And this is going to equal, if I solve for t again, y plus 3 divided by 11. And this will equal z minus 2 divided by 9. So pretty easy to write your two equations, or to write the equation of a line in space. Again, it's going to be parametric, it's in space, so you have your x, y, and z. And then if it's symmetric, you have to have a t in each one, and then it's just solving for t. Moving on to planes in space. For a plane in space, in order to write the equation, we need a point in the plane, and we have to have a vector normal to the plane. Remember that normal means perpendicular. So you need a point on the plane and a vector that is perpendicular to the plane. So we have a plane that contains our point, any point, it doesn't matter, so here's our point, and having a normal vector. So our normal vector, remember normal is a perpendicular vector, and normal we have a, b, c. It can be represented in standard form by this equation. So again, keep in mind, this is now a plane. We just wrote the equation of a line. Now we're writing the equations of a plane. For this situation, it's your normal vector, so you have a times x minus x sub 1. And x sub 1 is some point on that plane. Plus b times y minus y sub 1. Plus c times z minus z sub 1, and this is going to equal 0. So that's our standard form. Most of the time though, we like to write things, it'll be in general form. And what will happen with general form is here you're going to take and distribute your a, you're going to distribute your b, you're going to distribute your c. Well, x is your variable, but remember x sub 1 is a number. So really you're going to have a times x, and then this a times that x sub 1 or negative x sub 1, that's just going to create a constant. So it's just ax plus by, again b times y sub 1 is another constant, plus c times z, c times that negative z sub 1, that's another constant. So then we're just going to say it's plus d. And d takes the place of the three constants added together, and then this will equal 0. So when you write the equation, you do want it set equal to 0. And remember that this d is the sum of your constants. You have to make sure that you have your normal vector though here. So our normal vector coming up from here, we know our normal vector is ABC, and we need to have that normal vector, that perpendicular vector to our plane. So an example, we have to find the equation of a plane passing through this point. So this point is on our plane, and it's perpendicular to this vector. Well, perfect. Those are the exact things that we need. So, I like to write my vectors this way instead. Not that you have to do it, but to me it's easier. I don't know why. But to figure out what that constant should be, this d, we really have to go back to our standard form and distribute, and then in the long run we want our answer to be in general form. So we'll have 3 times x minus your x value there, so 3, minus 2 times y minus 2, and plus 1 times z minus 2, and this is going to equal 0. Well, when I write this out, I'm going to have 3x minus 9 minus 2y plus 4 plus z minus 2 equals 0. And then to write it in general form, we end with 3x minus 2y plus z. And then our negative 9 plus 4, negative 5 minus 2 would give us minus 7 equals 0. So in the long run, we do want to write our equation, clean it up and write it in general form instead of leaving it in standard form. So whenever you write the equation of a plane, I want it to look like this. If we have to find that normal vector, so finding n, what we did in the last section, 11.4, if we know two vectors in our plane, we can find a normal vector or a perpendicular vector by that, what we did in section 4, which if you remember is just our cross product. So using our cross product, we can do this. What has to happen though is we have to know two vectors in the plane, and they have to be in the same plane. Your two vectors have to be on that plane, because remember we said that the cross product, it was orthogonal to both of them. So to guarantee that this new vector is normal to the plane, the two vectors have to be in the plane. So we can use our cross product, and we know then that the resulting vector, is orthogonal or normal to both original vectors. Alright, so now the type of problem that we can do with this next example is we have to find the general equation of a plane, and our plane contains 3 points. Well, the idea here, to write the equation of a plane, we need to have a point on our plane. Well, we have 3 of them, but we have to have that normal vector. Well, to create a normal vector, we're going to have to use our cross product. So what we're going to call these points P, Q, and R. We can create 2 vectors on this plane. So we can call them vector PQ and vector QR. You can really pick any combination, but you can create the vector between the 2 points. So if I create vector PQ, I have 3 minus 2 is going to give me 1. 4 minus 3 will give me 1. 2 minus a negative 2 will give me 4. There is one vector on this plane. Then I'm just going to say QR. It doesn't really matter as long as you take a different combination here. And if I do QR, I have 1 minus 3, so there's a negative 2. Negative 1 minus 4, that gives me negative 5. 0 minus 2, that gives me negative 2. So now I have 2 vectors on this particular plane, and so when I use my cross product between them, I create a new vector that's orthogonal to both of these. Well, if it's orthogonal to these, that means that it will be orthogonal or normal to our plane. So our cross product, we have I, J, K, 1, 1, 4, negative 2, negative 5, negative 2, and cross things off, we would have negative 2 minus a negative 20. So negative 2 minus a negative 20, that will give us 18. Go to the next one and lightly cross these off. I have negative 2 minus a negative 8, and that will give me 6. I think that's right. On my work I have a negative 6. I screw up somewhere. I have a negative 2 minus a negative 8. That should be a positive 6, I believe. And oh, just kidding. It totally isn't, because the second one, remember this term always has to be the negative of it. So yes, it is a positive 6. That definitely has to be a negative. I wasn't thinking there for a second. And then our last one should be negative 5 minus a negative 2. Therefore, we should have negative 3. And here is our normal vector. So we have our normal vector, and you can use any point here. So then pick a point that you like. I just picked 3, 4, and 2, and because on there and I didn't have to deal with negatives. It doesn't matter which one you have. And now to write my equation, I have 18 times x minus 3 minus 6 times y minus 4 minus 3 times z minus 2 equals 0. Distribute 18x minus 54 minus 6y plus 24 minus 3z plus 6 is equal to 0. Therefore, 18x minus 6y minus 3z, oh boy, negative 54 plus 24, and then plus 6, so that should give me, I think, negative 24 there, is equal to 0. And this definitely works. When you check some of your answers, they will simplify, so they'll look for common factors here. In 18, 6, 3, 24, obviously a common factor is 3, so you could divide both sides by 3, and therefore we could say that our answer then is 6x minus 2y minus z minus 8 is equal to 0. And there is the equation of our plane. And that plane will contain these 3 points. And you could check them and plug in your points and make sure that it works, and it does. Okay, another thing that we can do is find the angle between 2 planes in space. So the angle between two intersecting planes is going to be between 0 and 90, because no matter what, when 2 planes intersect, one of the angles will be between 0 and 90 degrees, or 0 and pi over 2. And we want to use the angle between we'll be finding use the angle between our normal vectors. Specifically, if vector n sub 1 and m sub 2 are normal to 2 intersecting planes, the angle theta between the normal vectors is equal to the angle between the 2 planes, and is given by this equation. We have cosine of theta is equal to, this is absolute value of n sub 1 dot n sub 2. And so that is absolute value there, divided by the magnitude of n sub 1 times the magnitude of n sub 2. And this is absolute value, so then when you do the inverse of cosine, you'll always end up with an angle between 0 and pi over 2. You know that this is going to be that the 2 planes will be perpendicular if this dot product is equal to 0. Because remember that cosine of theta, if it's equal to 0, then theta is equal to your pi over 2. So they're perpendicular if n sub 1 dot n sub 2 is equal to 0. Then you know that you have 2 planes that are perpendicular to each other, or normal or orthogonal, or what they're using. The 2 planes could be parallel, and they're parallel if n sub 1 is a scalar multiple of n sub 2. So is a scalar multiple of n sub 2. So, type of question that we can have, for example, determine whether the planes are parallel, orthogonal, or neither. If they are neither parallel nor orthogonal, then we want to find the angle of intersection. So if we look at our first plane here, we know that this plane, if we look at our direction vector that goes with it, n sub 1 is going to equal 3, 1, negative 4. And we don't really care about that constant. But this is our normal vector for it. If we look at the second plane, n sub 2 is equal to the directional vector is negative 9, negative 3, positive 12. And obviously comparing these two things, how do you get, you should always check to see if they're parallel first. So how do we go from 3 to a negative 9 multiplied by negative 3? Well, if I multiply by negative 3, I end up there. If I multiply by negative 3, I end up at 12. Therefore, if we multiply by a negative 3, we know that these two things are equal to each other, or that the scalar here is a negative 3. Therefore, these are parallel, these two planes. Number 60, again, I like to write out my my direction vectors first. So I have 3, 2, negative 1. That constant doesn't matter. And n sub 2 would be 1, negative 4, 2. A negative 4, a positive 2. Well, looking at this, I can tell there's obviously not a scalar multiple that will get me from one vector to the other, because 3 to 1 would be multiplying by 1/3. That's not going to be the case. So we know that it's not parallel. We can check quickly to see if it's orthogonal or not using the dot product. And so if the dot product is equal to 0, great, we know it's orthogonal. Well, 3 times 1 is 3, plus 2 times a negative 4 is negative 8, plus negative 1 times 2 is negative 2, and this answer will give us a negative 7, which obviously doesn't equal 0, therefore it's not orthogonal. So now we have to figure out what is the angle between our two planes, and the formula is cosine of theta is equal to, remember, it's the absolute value of our dot product, so we plug in that negative 7, it's obviously going to make it 7. And then we have, looking back up at your formula, it's the magnitude of your two vectors multiplied together. So our magnitude here is going to be 9 plus 4, so it's 13, plus 1, so it's 14, times the magnitude is 1 plus 16, that gives us 17, plus 4 will give us 21. So what I did on my calculator, I just did 7 divided by parentheses, I used 2 sets here, but I typed this whole thing in first, so square root of 14 times, whoa, I forgot the square root here, square root of 21. And then your second cosine, second answer. And in this situation, theta, that angle between our two planes, is approximately 65.9 degrees. So, finding the angle. If we look back over this page, we did quite a few things. We wrote the equation of a line, which, just like any equation of a line, you need a point on the line, and you need your slope or your directional vector, and different ways that we can do that. We wrote the equation of a plane, and again, you need a point on your plane, and now you need a vector that's normal to your plane, and then we obviously have to know the equation for it. To find that normal vector, we can always use the cross product, which is pretty basic to use. Like, I forgot, remember that term always has to be the opposite, the negative of it. And if you have 3 points on your plane, you can create 2 vectors in the plane. Cross product, now you have a normal vector. And then you had angles between 2 planes in space. So kind of a lot of things that we were able to do on that first page. And maybe we'll make this into 2 videos, so you could take a little break here now. And then, so the first page will be 1 video. If you want to, then the second video for this section, we'll put it on a different one so you can refer to it maybe a little bit easier. Alright, take a little break and start the next video.